5 times 5 is?
25.
Yeah. Hey folks, welcome out there this afternoon. And whether you're listening to this online, it may be an evening, it may be a morning, it could be midnight, I don't know. But anyway, thanks for tuning in this afternoon. This time, I'm Ernie Roberts, and I am your host for this afternoon. And since we're going to go with afternoon, I'll call it afternoon session of Mathline. Now, it's a specialized segments day, so you don't get to call in, but you can still send us emails, and you can still send us messages on Facebook and all those good things. We'd love to hear from you. You can still like us, love us, and share us all over the place. But what we're going to do today, we're going to sit back, we're going to relax, we're going to do some math, and I'm going to go ahead and tell you. You might want to get a little pencil, a little paper out. I don't know if you need a calculator for today or not, but just in case, grab one, all right? And let's see what we are going to delve into on today's specialized segment topic. To be or not to be? A triangle. Oh my goodness, I thought we were going to have Shakespeare for a minute here. We're going to decide whether we have situations to make a triangle or not to make a triangle, and then if we have one, maybe what kind of triangle it could possibly be. To be or not to be. I like that. I like that. That is the question, and now let's see what's going on. Now, I have a blank sheet of paper here. Have you noticed that? There's nothing there. No, don't adjust your screens. Don't get nervous. I am going to put 3 little pieces, look like little straws there. That's kind of what they are, out here. Let y'all look at them. Magic, magic. And I want to make a triangle out of them. People say, oh, 3 sides, make a triangle. Boom, boom, boom. Now, remember what the title of the show is today, to be or not to be. Question is, looking at those, got an idea? Will they make a triangle? You say, what do you mean? Of course, there are 3 sides. You can make a triangle. And I always start looking at them and thinking, what can I do? I like to lay them end to end. By the way, that's going to be another stipulation we need to make. We need to make sure that our points go end to end. By the way, these are just good old stirring straws. And go like, well, maybe if I twist it down a little bit more and keep twisting it down, well, maybe this will work. Oh dear, still not getting there, is it? Pull it down a little bit more. Your eyes are better than mine. I'm beginning to lose my triangle business. I can't get it there. There's a problem. There's a problem. It looks like, even if I pull them down there, look, goodness, those 2 lengths, they're just way too short. We got a big gap there. So that didn't work. All right. Oh, by the way, some of you say, well, Ernie, it looks like it's a little off center. Now it really is. Now, we never could make that gap up in the middle. So there's a failure right there, okay? So that's one of the situations that can't be a triangle. Now, before I leave, sometimes when I do this for my students, they say, oh, after they've played up there in front of their student body friends and stuff, they said, I can do this. And we say, yay, we have a triangle. There we go, push that right up there. Well, you do, but not the ones I wanted to make. I want to use the endpoints there. So, and push that up there a little bit. It still doesn't work, does it? So, these little laid end-to-end moments don't seem to work, all right? Well, all right, keep that one around. Let's pick up a new straw, okay? Maybe that'll help. And if I put it up there, I notice, okay, that's the same length. They're all the same length. They come in the same package. So let's try this. Let's just do a little snip here. Doesn't matter where. There we go. Let's see if that works. Makes them a little longer because it looks like those were shortchanged, the ones we used there, the 2 little guys. So we know this one matches up. Let's see what happens if we bring it together. I bet we have a better chance. Let's see. I'm going to try to keep that there. Bring that down. Oh my goodness, it's going to be another tight fit, folks. Here we're going. Oh, they're almost there, but it went right through. Bring it out a little bit more there. Oh, we still haven't met. You know what? We never met. We did meet, but when it became a what? Well, it became a rolling little line here. Let's see. Put them together. Well, guess what? It doesn't make a triangle if they're the same lengths either, if they add, the things going on here. So something's still not long enough, all right? So maybe I keep one of them, and I get another one over here. Let's see. This one that we used earlier, how about, ooh, look what happens. This may have some hope, because when these 2 come together, they're a little bit longer. So let's see what happens if I push them out. Let's see if I can do this. It's going to be a difficult moment. The hand is not quicker than the eye on this one, is it, folks? Ooh, we're going to pull it up a little bit. But you get the idea. We're getting a triangle. So what's going on here? What's the fact that we're going to look at? And I'll push that up just a little bit more for those of you who are purists. So now we got point to point to point to point all the way through there. Why did it not work for these three puppies? Well, because they weren't long enough, right? So there's a little rule going on here. Oh, play with these. Y'all are going to turn on there going, whoa, what's he doing today? It's all over the place. What's happening here, I'm going to take these away because this is what I want to focus on. What's happening here is real simple. The two shorter sides have to add up to be bigger than the longer side. If you throw three numbers out there, 3, 4, 8, for example, that would mean maybe 3 inches for one, 4 inches for the other, and 8 inches. Can you make a triangle? Absolutely not. You can't. They're not going to come together. They're going to collapse. Let's go back to this figure one more time here, just to look at what we've got going here. So the deal is here, the smaller two add up to be larger than the third side. We have a name for this, all right? Let me go ahead and fill you in. Now I'll move these back just a little bit. We call this the triangle inequality. In geometry, you see this, but you know what? I think people in middle school, I think if you're in elementary school, you're going to be able to understand this pretty well, okay, without much trouble. So what's happening is basically the sum, which means we add, of the two smaller sides must be greater than the longest side. And that works for the most part. You say, what do you mean it works for the most part? Well, you can almost have when I say the longest side, we could have an isosceles triangle there, all right? So we could be looking at two sides that are the same length. For example, both sides could be 8. They could be the longest side, okay? Or both sides could be 7. That could be, one of those would be the longest side. But guess what? If you add anything plus that other 7, or if you add anything plus that other 8, you're going to make it bigger than the third side, right? 8. So it works. It works. So let's look at some situations. Let's look at some combinations of numbers just to make us think a little bit. Now, I know some of you are going like, well, Ernie, I thought we had that a squared plus b squared equals c squared relationship. Well, here we are dealing with any triangle. The a squared plus b squared equaling c squared, Pythagorean theorem, yes, we've got that in our brain. That has to do with right triangles. So again, when we work with the triangle inequality, we're just trying to figure out not if it's a right triangle, we want to know, do the lengths make a triangle? So the requirement again, you got it. The two shorter lengths must add to be what? Greater than the third length, or the what? Longest length, all right? So let's take a look at this. Let's take a look at an example here. Can the segment lengths 4, 7, and 13 form a triangle? Can they? You all just saw proof of that one way or the other, right? We just did on our little screen here. How about it? The question being, is 4 plus 7 greater than 13? And let me put that. Is 4 plus 7 greater than 13? The answer is yes, you've got a triangle. If the answer is no, guess what? You don't have a triangle. Pretty straightforward, isn't it? It's not a hard concept today. This is one of those things that after you do 2 or 3 examples, you're going, okay, what else can we do with this? And we'll show you, of course. We have 11 greater than 13? Absolutely not. That's a no. So these cannot form a triangle. That was pretty straightforward, wasn't it? All you got to be doing is to add some numbers and then check yourselves. Now, what if I said 4 plus 8? What if I said 4, 8, and 13? Still not good enough, is it? 4, 9, and 13. It would still collapse. It would make just 2 line segments that would be laying right on top of each other, but not making a triangle. It's like what we call that segment addition postulate. Remember where you said the small parts add up to give you the long segment? That would be what that situation would be if we had 4, 9, and 13. But once we get beyond 9, all of a sudden life is good. And now I want to point out something to you with when we get beyond 9. 4 plus 9.1, does that work? 9 and 1/10? 13 and 1/10. It's going to be a real interesting looking triangle, but it's still going to work, all right? How about it if we get 9 and 100th, 9.01? It's still going to work. But it's going to, again, look very strange as a triangle. Probably not very good with our straws, okay, because they like to roll around. It would be very hard to get them to stay together. But you get my idea. The idea is that it's not going to just be integer values, all right? We're going to be able to use some numbers that are decimals and fractions and so forth. So that's our start, all right? So let's just do a couple of quick practices. I think I've already given away the answers to the rest of the, no, not the rest of the day, but the next two anyway. Let's take a look at them here, all right? We got 3, 4, and 7. Bingo. Anybody can do this mentally? Mental math time? Yes. The question is, 3 plus 4, is it greater than 7? Question mark. Is 3 plus 4 greater than 7? Absolutely not. They're equal. Okay, it's got to be greater than. It's going to have to be greater than on this thing. So we got 7 greater than 7, which everybody knows that's not true because they're the same number, right? So guess what? No triangle here. This is one of those situations where the two lengths would collapse to make the longer segment. And we'd have a segment addition postulate situation. So yes, there's a connection between this triangle inequality and what you guys in geometry learned called the segment addition postulate, where you have the little 3 plus the little 4, and they're all in the same line. They're collinear segments, points, and they small 2, the 3 is small, the 4 is small. It adds up to give you the 7. And that would be that good old angle addition, segment addition. We're going to get angle addition another day on the show here, but segment addition postulate. And another thing about that segment addition postulate, sometimes you call it definition betweenness in some of the older textbooks. So just so you know, that's what we're going back to. So this one is no triangle. Actually, the segments are going to line up and be beautiful collinear points, which gives us that segment addition business. Now, how about the next one here? Gave it away again, probably. This becomes really easy. You say, are we going to do this all show? No, we're going to be using it all show, but we're not going to do it all show here. So we got 3 plus 7. No, we got 3 plus 5, right? Because we want to check the two shorter lengths here. And we're going to ask, are they greater than 7? Because we know if we had 3 plus 7, my friends, it's going to be bigger than 5. Duh, of course it will. We had 5 and 7, it's going to be bigger than 3. The only place where this can go astray is with the two smallest segments being less than or equal to the largest of the segments. This time, we win. We get 8, which is greater than 7. Whew. Finally, we have a triangle. Yes. Yes, yes, yes. It is a triangle. Not a question mark, is it? We know that for sure. We'll just make that exclamation point. How about it? Since we got one there, we get one here. So you got it right there. That's the story. Again, these two small lengths simply, very simple, have to add up to be larger than the longest length. It's easy, isn't it? Very easy. So you said, Ernie, what can you do to make this difficult? You always seem to be doing that. Well, I could throw an X or two in there, but I'm not yet ready for that, all right? We may catch that on another show or during our call-ins and stuff. We may throw that up as a problem of the day. But let's take a look at a little situation that we can deal with here, all right? And goes along with the course of what we've been doing. It says, find the range of values for a third side of a triangle if the first two sides have lengths of 5 and 9. Okay. Now, let's think a little bit. I know, yeah, I almost hate to think about it. We got 5 and 9. And it says, find the range of values for a third side. So in other words, we want to take this third side up as far as we can go. But we also would like to see how low can we go. It's kind of like doing limbo here, all right? Geometric limbo. Could that be a new book? No, it could be anything. How are we going to get there? Now, some of you are going to say, oh, well, these have to be between 5 and 9. Well, that could be a possibility. That could be option. But is it really the only option? Let's look at some numbers. What if I gave you the number 2? How about it with the 2? That's on the low end. If I have 2 and 5, does it add up to be, you see where I'm going? Does it add up to be greater than 9? No, it doesn't, so it's not a good answer. What about 3? 3 plus 5, it gives us 8, which is getting closer, but still not a good answer. How about 4? 4 and 5, we have now equaled 9. So think about it. You need to be just a little bit above it. So you say 5? That means you would, no. How about it? 4.5. 1, 4 and 1/10. How about 4 1/4? How about 4 and 1/100th? Ooh, starting to think a little bit, right? So we kind of have this 4 that we're going to put a little question mark over there. How are we going to deal with that? Because we don't want exactly 4, but we want to get as close as we can. Theoretically, we could get real close and real personal with that 4. On the other side, let's talk about what's going on the other side. Then we'll come back and combine these, okay? And so you're going to find it's not so bad. What about this upper limit? How about the number 10? Okay, now forget 4. Say goodbye to 4. Put your finger over something. 5 and 9, 14, right? Is 14 greater than 10? Yes, it is. So 10 is a good answer. Keep thinking. How about it? 11. 5 plus 9, 14. Sounds like 11 again. It's going to work, right? 5 plus 9. Let's go back again. 5 and 6 gives us 11, right? So we're good? All right, what about 12 going in there? 5 plus 9 is 14, so we're still good. How about 13? Still good. 14. Uh-oh, we have matched it. Now you see where we're going on this? So I'm going to say the same question mark. 14 makes it collapse. But how much under can we go? In other words, how high are we going to be able to go here? We're going to almost hit 14. So think like what we did with the 4. We're going to look at 13 and 9/10 or 13.9. That's good. It's a good answer because 14 is bigger than that. What if we go, how about it? 13.999? Still good. You get the idea. In other words, we're going to figure out what to do with that one too. It's kind of the same story. It's just on the other end. So here we go. We got 4. And we know it's got to be somewhere between 4 and 14. So where do we go from there? That's it. Any numbers as close as we can get to 4 without hitting 4. Any numbers we've got as close as we can get to 14 without taking out 14 there. Now I use the integers just to give you a feel for what's going on. But I want you to realize once we break even here, it's not just about integers. It's not that we're going to put the number, 3 and then the number 15 here to make it work. It's numbers that get really, really close to 4 as well as 14. So there's your range of values. And keep in mind, we didn't ask for what the specific values were. We wanted to look for the range, the total range possible. Now, if they ask you to give just integral values or integer values, you would have used the numbers that were not including 4 and 14. You would have gone with 5, 6, 7, 8, 9, 10, 11, 12, and 13. All of those would have been good answers that would have kept your triangle inequality intact. So you see what it's all about. Now, before we leave this little piece here, can you see a connection between 4 and 5 and 9? Forget 14. Forget 14 right now. This is where I like to get things going, where we make connections. In other words, how do you get to the lower limit? You just simply subtract these numbers from each other. Right. 9 minus 5 gets you to 4. You can't get to 4 per se. You get as close as you can to it, all right? But that gives you that lower boundary there that you're going to be able to work with. Here is the upper boundary. Well, look what happened. 5 plus 9 gave you the 14. So this is really a pretty easy thing to look for, isn't it? When you've got that concept, it's adding and subtracting to find the upper and lower boundaries, all right? So let's do another one, all right? Let's try one more here, and we'll see how we're doing. I think you guys can probably figure this one out real quickly. Maybe, maybe not. We'll try it, okay? Let's see what we got here. It says, what is the range of values for a third side of a triangle? So this is one of those crazy questions. Oh my, we gave you isosceles. At least isosceles. Isosceles for sure. 8 and 8, 2 sides. So how about it? 8, 8. The question mark is going to be what numbers and what numbers here. Now keep in mind, we're not going to reach this number. We're not going to reach that number. We're going to do the same thing. We use the good old combined and inequality there, all right, to see what's going on. So here we are. That's kind of interesting because it is triangle inequality we've been working with. This is a different layer of inequality for us, okay, to finding that third side. Well, what do you think? Throw me a number. I'll throw you a number. 4. 4, 8, that works. 4 plus 8 is certainly greater than 8. In fact, if you put any number here, what's going to happen? It's going to be greater than 8 unless you do what? Yes, put a 0. And all of a sudden now you have 0 plus 8 and you get 8. Now you can't go negative here because we're talking lengths of segments, all right? So what this is going to tell me is you say, Ernie, doesn't that make it collapse? It does if you put a 0 in there. But if you go just a little bit above the 0, you got a triangle. Maybe you put in 1/10. You put in 1/100th. It's going to be hard to see that little side because it's very, very small, but theoretically it's going to work. So what about the upper end? Try number 14. Well, 8 plus 8 certainly is greater than 14. If I put a 15 in there, life is good. 8 plus 8, 16, so it's back to 15. Oh, guess what? If we put 8 plus 8, we get that 16. You see what's going on here? That's what I want you to see. Again, if you subtract the 8s, you get to the lower limit. If you add the 8s, you got to your upper limit. Now, your upper limit means you don't want to go over it and you don't want to get to it. So once again, we're going to put that in a nice little combined inequality form. 0 less than x, which basically means x has got to be positive. It's going to be greater than 0. And it's got to come short of 16, like maybe 15.9, 15.95. It can be that close, all right? So that's why we cut it at 16. We just don't get there. So do not put equals to underneath those because then you got a little problem because your triangles will collapse. All right, how about it? To be or not to be a triangle? That's pretty interesting stuff. And it's also, if you just play with that, if you did something with it, my goodness, guess what? It's like using your eyes. It's like using your eyes to figure it out. So let's go with another little problem here, all right? Got a question. I always have a question here. And let's go to a grid. We haven't done a grid yet. But it says do the points -3, 7, 4, 6 is another point, and 0, 3 form a triangle. We know you're going to have 3 points on a grid unless they just lie in a straight line, which could be possible on this show. You know how that works. Then we might have a situation where it's not a right triangle, or at least not a triangle. We know it's going to be a triangle as long as we don't get all these things collinear points. So let's check them out here. -3, and we're going to go up 7, right up there we go. There's your first point. We got 4, 6. We're going to slide over here, over 4 and up to 4, 6. And then we're going to also pick up 0, 3. And I'm hoping that I have put these things in the correct options here. I think we have them in good shape. Now, we didn't ask if they were going to be isosceles or equilateral or anything like that, but there we have it. Now, let's line it up a little bit here. Let's draw these things together. There is a nice little line segment. There's one of the sides. Here is another line segment. And going across here, we've got a second one here, all right? Question is it a right triangle? You look at that and you go like, Ernie, it would be nice if you had just lined them up and made horizontal, vertical sides. Didn't work that way, did it? So we've got to think back a little bit. Now, you've already decided, we know it's a triangle because look how the points are. So obviously these two pieces are smaller than that one, so this would be like the a squared plus b squared equals c squared if we're lucky, okay, if we have that situation happen. Well, you know, I don't know if we're lucky or not. You want to find out? I think we want to find out, don't we? Got what, just a couple of minutes here, guys? So let's use an easy approach. And also I'm going to tell you, you could find distance on all 3 of these and test them out using Pythagorean theorem. And if they are equal, a squared plus b squared does equal c squared, then life is good. But what we're going to do instead, we're going to use slopes. Because there's another way you find out a right triangle, correct? Or right angle. And if you got a right angle, you got a right triangle. You look for opposite reciprocals. How about that? So let's play the slope. This one going from here to here, we go down 1, 2, 3, 4 over 3. So this slope here of this one, I'm going to put it right up here, is a -4/3. All right, that's our slope. Check this one out. 1, 2, 3. Oh my goodness, that's over 4. So we have the slope equaling 3 over 4. Now you say, wow, how about that? So we definitely have a right triangle. Could you find the lengths That's where the crazy distance formula, or you could just use Pythagorean. In other words, make you a little right triangle. You know, we just did rise and run. We just did the rise and run. So this would be like creating here and here. We could go, that's 4, that's 3. That's coming down, -4, but it doesn't matter because we're going down, right? Just use the distance formula, square it, add them, get a square root. You know what that's going to give us? That's going to give us 5. That's going to give us 5 here. And I'll go ahead and give you a hint. This little guy up here, if you run the distance formula, or if you do the rise over run, square it, Pythagorean theorem, you're going to get 5 square roots of 2, or the square root of 50. And that's another way to prove. Another way to prove that thing's a right triangle. So those are some of the good things about triangles. So once we get one, sometimes we can figure out if it's a right triangle. And you know what? We can also figure out acute and obtuse, all right? But thank you for tuning in today. Hope you got a little bit of that to be or not to be or triangle and got it down. And you know what? We'll be back again, and we will see you next time.